In this example, we're going to look at how we can use the stream function to solve a particular problem. So we're given the velocity components of a steady incompressible flow field are given as u equal a equal to y and v equal to b times x. And we're asked for three things. One, we're asked if continuity is satisfied, b, if the flow is irrotational, and c, to sketch the streamline passing through the origin. Okay, so to get started, we're going to look at the continuity. So let's look at part A. Switch colors here. Okay, so continuity satisfied. So our continuity equation simplifies to du over dx plus dv over dy equal to 0. Right? So we can just plug in our solutions here. So we can say d over dx of ay plus d over dy of bx equals to 0. And then you can pretty immediately see that the derivative of ay is going to be 0. So this term is 0. And the same thing here. This term is 0 as well, because the derivative of bx with respect to y is also 0. So continuity is satisfied. Check the answer there. For part B, we're asked if the flow is irrotational. So B, we're asked if it's irrotational. To satisfy irrotationality, we need del cross V equal to 0. We do not have a z component, so that means that the only thing we need to satisfy here is that dv over dx minus du over dy equals 0. We can again plug in, so we get d over dx of bx minus d over dy of ay equal to 0. Okay, we can take those derivatives, they're really easy. This goes to b minus this goes to a equals 0, and we can say that b equals a. So the flow is irrotational only if b equals a. So we can say that irrotational if and only if a equals b. Okay, so that's part B. And then part C, we're asked to sketch. So the easiest thing to do here is to solve for the functional form of psi. Okay, so the first thing we can do is say that, plug in our definition. So d psi over dy is equal to u is equal to a y. Okay, and we can integrate that. It's pretty straightforward integral. And so you get psi is equal to a over 2 y squared plus some function of x. Okay, so where our function of x is our constant. Okay, so that's the first part, and now we can plug in for the second part. So we say d psi over dx, negative d psi over dx is equal to v is equal to bx. Alright, so now we can integrate that. You get psi is equal to b over 2, negative b over 2 x squared plus some function of y. We can combine these two to get our functional form of psi. So we get psi is equal to a over 2 y squared minus b over 2 x squared plus some arbitrary constant that we don't need to worry about. In fact, let's go ahead for this particular problem and set that equal to 0. Okay, so this is our functional form of our equation. Now, if we want to sketch the streamlines going through the origin, the easiest thing there to do is set psi equal to 0. So we're going to set psi equal to 0 and solve to get what that stream functional form is. And so When we do that, we get a over 2y squared equals b over 2x squared. You can divide through by a over 2, so the halves cancel and you get y squared equals b over a x squared. You take the square root, we get y equals plus or minus the square root of b over a x. Okay, so these are lines going through the origin, and they have a slope of plus or minus b over a. And so I'm not going to draw specifically the units on here, but we can visualize that as a line going through the origin here and a line going through the origin this way, and the flows are actually in these directions here. Okay, so that's what the streamlines look like going through the origin for this particular problem. Okay, so going back and recapping, we said that the flow does satisfy continuity because the two terms are both 0, and that equals 0. The flow is irrotational only if A equals B. All right. And then finally, we solved and sketched the streamlines at the origin. So that's an example of how we can use the stream function to solve for a couple of the different, for what a flow pattern looks like. And we could do this for some other values of psi by just setting them equal to something and then sketching them out. Okay, that's it for this video.